they found a black hole, right?
Yes.
And the black hole is pretty amazing. And about 200 people were involved in taking a picture of this black hole. This guy is particularly happy. He is holding in this stack of things. There's a stack of hard disks that he is carrying in this grouping here. It's half a petabyte of data. A petabyte is a very large amount of data that you can't imagine. So it's not a megabyte, which is a million. It's not a gigabyte, which is a billion. It's not a tetrabyte, which is a trillion. It's 1,000 trillion, which is what a petabyte is. That's the amount of data that is sitting there on the table. And that data was required to take the picture of the black hole. You accumulated a lot of data. I'll explain how in a bit. But you accumulated a lot of data, and then you brought all the data to the computer. But there was so much data that you couldn't bring it to the computer over the lines. You could not bring it over the internet, because the internet, amazing as it is not capable of transmitting this much data in a reasonable fashion. So what they did is they put these hard disks on a 747, and they flew it halfway across the world to bring it to the computer that needed this data to create the picture of the black hole. The way the guy who created this project in the first place, the way he describes it, is nothing can beat the bandwidth of a 747 carrying these hard disks. In fact, he literally said, carrying these hard disks and walking like this is faster than the internet can move that data. So literally, SneakerNet is faster than the internet is when it comes to that much data. And it took that much data to create the image of the black hole. That much data times probably 50 to create the image. And then a couple of years worth of computation and work, and finally they came up with the image. The image of a black hole. So let me show you, if I can. So that's the Earth, and the thing about the Earth is, in order to take a picture of the black hole, they literally made a telescope as big as the Earth. In order to take a picture of something that is very, very far away, they use the entire planet Earth as the telescope. The biggest telescope that was ever made was used to take that picture. Okay. What's the definition of a black hole? Einstein figured out in about 1916 that light could be bent by gravity, and in this class we have actually, in front of this blackboard, I have proved to you that light can be bent by gravity. It's quite an amazing demonstration, and it can be done in 2 minutes. So Einstein was he was no Einstein in the sense that anybody who had the idea that he had, which of course he was the only one, but anybody who had that idea could have been the Einstein that he became. Okay, but all he said was, "Oh, I'm not even going to do the thing that he said, because that takes time." Light gets bent by gravity. Good. The more gravity, the more it gets bent. Okay, so sometimes the light can go and get bent. What happens if there's a lot of gravity? Then the light can get bent even more. What happens if there is so much gravity that the light gets bent and actually falls into where the gravity is? then the light doesn't get out. The light comes in but doesn't come out. So anything that's inside this thing, which was later called a black hole, anything that's inside can't get out, because if it was trying to get out, it would go and fall back in. So no light can get out of something that gravity bends the light so it can't get out of. Okay, that's what a black hole is in small order. Yes?
What is the event horizon?
Okay, now the event horizon is a lot of fun, okay? It's one of the most, no one ever tells you this one, but I had a teacher who told me this one, and it's the best story, I think, of a black hole. Nobody ever tells this story. Okay, so when you fall into a black hole, you've heard things that time slows down and stuff like that. So you go faster, close to the speed of light, and time slows down. And so there's a time thing going on with respect to relativity. So it wouldn't surprise you that there's some sort of time sort of thing going on with respect to general relativity. And it turns out that as you fall towards the black hole, and you look out on the universe, okay, because the universe is back there, and the black hole's here, and you're looking back on the universe, and your watch is keeping normal time, because it always keeps good time. Good watch, always keeps good time. But the universe is time, and the universe starts to speed up, and so while you're looking out, you could see that as differently. You could imagine that all this light is falling in on you, and the light that's falling in on you is becoming harsher and harsher and harsher. So more and more and more stuff is falling in on you, and it gives you, and everything becomes very blue, and then X-ray, and the universe is falling in on you, light ray wise. But not only that, but time wise, the universe is falling in on you, and time is speeding up. Time is speeding up. Well, guess what happens as you approach the event horizon? Time continues to speed up. Time speeds up so much that when you pass the event horizon, you have passed the end of time. T equal infinity. Infinite amount of time has passed, and then you fall into the black hole. As far as you're concerned, you were due to fall into the black hole around 12, you did, and the universe went from now to infinity and beyond. All the time in the universe has passed, and then you fall into the black hole. But as far as you're concerned, it just takes you a couple minutes to fall in, normal rate of speed, you just don't notice it at all. The end of time can be experienced. Another way of saying that, however, is really interesting. If the end of time occurs as you fall through the black hole, then, if you will, nothing falls into the black hole, because it takes an infinite amount of time for something to pass through the event horizon. That's even crazier. Okay, we're talking about what you call a non-rotating black hole. This black hole rotates, they all do. So this is theoretical, based upon a non-rotating black hole. So the end of time occurs, it takes an infinite amount of time for anything to fall in, and if you were the one who's falling in, you would go past the end of time quite blithely, and then you'd be inside the black hole. And here's the interesting thing about this black hole. This black hole is very big. It's bigger than the black hole that sits in the middle of our Milky Way. Our Milky Way has a black hole that's 4 million suns together, 4 million solar masses. This one is 6 billion solar masses. It's much bigger than the black hole that's in the center of our Milky Way. As such, it's actually very large. It has very wide diameter. Its diameter is so large that the black hole itself is the diameter of our own solar system. And because it's very large, the diameter, the black hole is much more gentle to anybody who happens to be falling into it, than a very small black hole. You can make black holes as small as a star. A star, when it explodes, can literally create a black hole that's the size of a star, 1 solar mass, not 4 million, not 6 billion, for 1 solar mass. If you fell into a black hole that was 1 solar mass, you would not be happy. It's the same thing would be true, end of time kind of business, but you would be quite annoyed at the phenomenon because the tidal forces are such that your feet would be subjected to more gravity than the top of your head. And because of that, you would be pulled into a string. And they call that phenomenon spaghettification. Spaghettification is the phenomenon of falling into a black hole, and it's not something you want to do if you're busy investigating a black hole. Let's say you've decided that you're going to say goodbye to all your friends and relatives, you want to enter a black hole, you decide to enter one that's 1 solar mass. Not a good idea. Before you get there, you're going to be spaghettified long before you get to inside the black hole, even though you do pass the end of time. Yes?
If there's a black hole in the Milky Way, in our galaxy,
Yes.
which is far closer than
Yes.
this one, why'd they choose to photograph that one rather than ours?
I'm going to answer that question. The question is, why do they photograph something that's further away than something that's closer? I'm going to answer that next, but I want to finish the little story, okay? Because I like this story. Okay. But if you're falling into a supermassive black hole the size of 6 billion stars, the hole is the size of this solar system, and the spaghettification thing doesn't happen. The difference between the gravity on the top of your head and your feet is minuscule, so you don't feel the tug that would turn you into a noodle. So if you're going to investigate a black hole, that's the one you want to visit, because you can blithely fall into it. You certainly, by the time you reach the center of it, wherever that is, and however that is, you probably not be pleased. And you certainly would have no way of sending back information to your friends because it's a black hole and nothing gets out. So you would be the first person to enter it, and you'd also have no way of explaining it to anybody else. Which is why we don't know we don't have no idea what's inside these things. Literally. The laws of physics are absolutely beyond our ability to calculate them, and we don't know what goes on inside of them. And anybody who tells you they do, they don't. It's a complete mystery. But now the question that you asked.
Yeah, is the process of...
Well, I'm going to answer his question.
Oh, I'm sorry.
Okay? Okay. So, the question is, why look at one that's 53 million light years away, when you can look at one that is only a few tens of thousands of light years away? Why not look at the one that's closer? And the reason that you choose to look at the one that's furthest away is it's 1,000 times bigger than the one that's close, and the one that's close is 1,000 times smaller. So if you looked at the one that's close, it's 1,000 times smaller, it's 1,000 times closer. It's more or less the same deal as looking at the one that's far away, 1,000 times bigger, 1,000 times further away. The image that you would get from both of these is about the same size in terms of the resolution. The image they take of the black hole that they're going to take, they're working on the one in the middle of our Milky Way. That image is going to be exactly the same resolution as the one that they already did. So that's why they're doing it. Yes. No.
Yeah, is the process of spaghettification
Yeah.
The same as what they call the string theory?
No. No.
Think about it.
No. Is spaghettification the same as string theory? No, not at all. But but to explain to you, not that I'm going to, but string theory is about strings that are extremely small. You can't see them. Nobody has ever seen them because they exist in the minds and fantasies of cosmologists who have no reason to think that they exist in the first place, except that the math is beautiful. Okay, and if the math is beautiful, who could deny it? Because the universe seems to be arranged according to math. If the universe says, "I am very mathematical, find me." So when they find really beautiful math, they say, "I think we found you." You know, even though they have no evidence for it, and really almost no hope of evidence for it. There's nobody who's proposed a theory, an experiment that says, "I got an idea how to find the strings." Nobody has one of those ideas yet. So, did you have a question? I forgot your name.
I have another one.
Oh, you have another one. Okay.
Are all of the suns in a galaxy falling, or some of them at least, falling into the black hole within a galaxy?
Are all the suns falling into the galaxy, into the black hole? Is that happening? Well, first of all, no. And second of all, they had to, because in some way or other, we got 6 billion solar masses sitting inside the black hole. So the question is more like, is it happening now than did it ever happen? So in the past, were stars falling into the black hole, and it's not clear that they were stars that were falling into the black hole. The universe is made up of stars and the gas from which the stars are formed. And it turns out that in general, there's more gas in the universe than there are stars in the universe. So when you look at the Milky Way and you see all sorts of stuff, there's a lot of gas. It's probably more gas than there are stars. Certainly in M87, there's a lot more gas. So what's falling in is the gas. And stars don't fall in because this is what happens with a star. A star goes, I'm thinking of taking a journey, and I'm headed right for the black hole. I plan to miss it, okay, by just a teeny little bit, and then I'm going to go scooting around and come back out, okay? So I'm just going to skim by and come back out. And that's the star's plan. And you know what happens? Nothing. That's what happens. It goes in, it scoots, and it comes back out. It does not fall in. When it gets closer to the black hole, it doesn't go, I've been captured by the black hole, help, I'm falling in. That doesn't happen. It's an orbit around the black hole. An orbit is an orbit is an orbit. The orbit is an ellipse every time. It doesn't fall into the black hole at all. Only way it would fall into the black hole is if something disrupts it from doing the ellipse thing. And the thing that can disrupt it is gas that gets in its way, so it slows it down so it falls in, or if it gets really, 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 really close, then gravitational waves can be emitted by the thing, and then, yeah, it can get closer because it's losing energy to gravitational waves, and then it falls in. But basically, as long as you don't, play tag with the black hole, you're not going to fall into the black hole. And so they don't. Yes.
I thought that some of the headlines said that this black hole had swallowed galaxies. Is that just right?
No, it's this black. Think about this. Has the black hole swallowed galaxies? It's 200 times big, more massive than the Milky Way.
Right.
Okay. It didn't do that by simply being kind to other galaxies. Okay? What it did is it ate other galaxies. Galaxies in general are voracious eaters of other galaxies. Our galaxy currently is eating at least one galaxy. Our galaxy's has been disrupting a nearby galaxy that we only noticed it because that galaxy is literally spread across the sky. And we only realize, our galaxy did that to that galaxy. That galaxy is literally right hanging over our galaxy, and it's being currently disrupted by ours. So our galaxy is eating that one. And our galaxy eats other galaxies. That's how we got here.
But they're not going into a black hole.
Not going into a black hole, just becoming part of it. Right. Because the gases, see, if I throw two galaxies at each other, all right, they're going to miss each other, even if it's a direct hit. Because what happens is there's so much space between the stars, the chances of any two stars hitting one another when you throw them at each other is 0. What happens, though, is that there are gases in the galaxy. I told you, there's a lot of gas. These gases are ionized. Ionized gases they do one thing very well. They obey the laws of magnetism. So if there's magnetism, and there's magnetism everywhere in the galaxy because the stars make magnetism, because they rotate and they make magnetism. And the magnetism is all throughout the galaxy. And the little ions that are ionized, they are constantly responding to the magnetic field of the galaxy, and other ions from the other galaxy are responding to the magnetic field of that galaxy. And when the two galaxies pass one another, the magnetic fields get involved, and these ions, which were in separate galaxies, they start to interact with one another, and they pull the galaxies together, not the stars. The gases slow the galaxies down, so they actually, when they hit, they slow down and merge. Not the stars. They don't have anything to do with it. So galaxies merge. That's how galaxies are born. Our galaxy is big because it's a pretty big eater. M87 somehow or other had an enormous meal years ago. It happens to live, let me, if this doesn't work at all, this might work. It happens to live in that Virgo cluster that we were talking about, which is, assuming that anything shows up on the screen. Here, there's that Virgo cluster I'm going to pull out so you can see it. You see? That's the cluster that M87 lives in. It lives in a cluster of 2,000 galaxies that it has not eaten yet. It's the biggest one in that cluster. You can believe that cluster was bigger earlier, and M87 had lunch quite a number of times at the expense of other galaxies. And that's probably how it got its supermassive, incredibly massive black hole, because it sucked up other galaxies. So yeah, what was your question again? The answer is yes. What was the question?
Did it eat galaxies?
Does the galaxies eat galaxies? Absolutely, all the time.
How dense is a black hole?
That's a very good question, and the answer is infinite. Infinite. In the sense that the space. Imagine this space. Imagine that you have a piece of rubber, neoprene rubber, and you push down, and the sides become steeper and steeper and steeper. And imagine you pushed it down and down and down until it essentially went on forever. Okay? So at the end of forever, how dense is it? At the end of forever, it's infinitely dense. So nobody knows what's going on inside that hole. Okay? Maybe they all just say, let's stop falling in, and everybody will have a party. Who knows? Where does all that mass? It's all falling in. There is nothing. This is the thing about what they notice. There's nothing in the universe that can stand up to the force of gravity when it's concentrated that much. So nothing can stand up. Look with me. I'm standing up. There's gravity pulling down on me right now. I'm not falling through the floor. Why? Well, there's a floor. It's strong enough to hold me up. If the gravity was greater, I would break through the floor. And I would have to find something else to be standing on. It turns out that if you make gravity strong enough, nothing can stop anything from falling in. And that's why black holes get invented in the first place. The star that started all this mess is holding itself up. The sun is got a surface. That surface is sitting on something below it. Why doesn't the top part fall into the part that it's sitting on? It's because there's enough pressure of the gas underneath to keep the gas that's above it up. So literally, this part is being held up by this part. Okay? But if you compress it more, then this part can't hold up this part, and that together they fall into one another, and they can't stop because nothing will stop it. Eventually, there are some things you can form a white dwarf star, which is like the result of of things falling in on one another, and then it stops. So you get, if our sun became a smaller star because it fell in on itself, it become a white dwarf about the size of the Earth. Then if it really fell on itself because it couldn't, because the white dwarf wasn't strong enough to hold it up, because the white dwarfs are only so strong, then it would fall in even further, and it would become a neutron star. And a neutron star, the size of our sun, is exactly the size of Manhattan Island. Manhattan Island, you could take the entire sun and fit it into Manhattan Island, and it would be a neutron star, and you think that's good enough. But if you added a couple of more suns to that, it couldn't hold itself up either, and it would fall into itself, and nothing holds itself up, and you get a black hole.
So a black hole sucks things.
So black hole does no such sucking.
No?
No sucking. Got to get that word out of the idea. It cannot hold itself up, but it doesn't suck any more than our sun sucks. If you think that our sun is sucking our planet Earth, then you would be right in saying the black hole does. But if you replace the sun with a black hole of exactly the same mass, aside from the fact that you'd get very cold very quickly, there would be absolutely no change in your daily life. Okay, because you'd still be going around the sun once a year. You'd freeze to death in a few minutes. I don't know. It'd be interesting to know how long it would take you to freeze to death. I think it would take you about a day, for the whole Earth to solidify into just a giant ice ball. But anyway, where was I? I have no idea. Ask me a different question, and I'll know where I was. I had some train of thought. I love being diverted from these trains of thought. Let's see. What?
Why don't you explain what string theory is?
I'm not going to explain what string theory is in a class about black holes. No, please, I can't. Please, no.
She doesn't understand.
No, but I really don't want to do that in the middle of a black hole thing, because that would divert the few minutes I have left to explain it. There's a ton of things I haven't explained about black holes. I'll try to do string theory. Elaine, I don't know anything about string theory, but I will try at some point to say something about it. Okay, just not at this juncture. Okay. And I know you're always asking the same question. Explain string theory. So it's not like I haven't heard you.
I just wanted her to understand the difference between spaghettification.
Well, string theory is about 11-dimensional space that theoretically exists in some people's minds, and spaghettification is about your body being drawn into a noodle, which is visible, invisible noodle, real, as against on somebody's wet dream. So the business about, I know, angular, why the resolution? Okay, the thing that we didn't talk about is this Earth. It was called the Event Horizon Telescope. The Event Horizon Telescope is what did all this. Okay, so the Event Horizon Telescope is, there's a picture, if it shows up. That's nice. It was part of the movie at this moment. Excellent. There's the black hole, okay? There's the Earth, and there's the Event Horizon Telescope. And what it is there's a series of telescopes, like 7 or 8 telescopes, that are situated around the Earth. And they are big, massive telescopes that are that were built previously for other purposes, because basically, if you want to observe the skies, you observe the skies in various wavelengths. You look at optical, you look at X-ray, you look at gamma ray, you look at radio waves, you look at infrared, you look at ultraviolet, you look at every different kind of telescope there is to observe the sky. It's magic. We only use our eyes. We have visible light. It's only part of the spectrum. The spectrum goes on forever. Radio on one way, gamma rays on the other way. They built radio telescopes, one of many types of telescopes. These telescopes are very expensive, so they use the planet Earth. And at the beginning of this lecture, I showed you what the telescope really looks like. And the telescope really looks like that. That is, you point one of the telescopes at M87, and then you take some data, okay, from the telescope, and you record it on hard disk. But that's only one telescope somewhere in the world. And then other people elsewhere in the world at the exact same time are recording their data from their telescopes. And so using jet planes that travel faster than the internet, all that data is brought to one computer center. And that data is recombined in such a way that, let's say, as to construct a Earth-sized telescope. And how do you construct an Earth-sized telescope from those things? What you do is, let's say that you've got light coming from there, and here I'm a telescope, and I've got the light, and it's coming from there. And now there's another telescope on the other side of the Earth, and the light coming from there comes the same light from the same thing. It's the same piece of light is coming this way, and I get that same piece of light, but I get it delayed by a little bit because I'm a little further away. So I have an atomic clock that I have set up. So I know exactly what time each of the rays of light arrived at my telescope that I record on my computer. And I say, aha, this ray of light arrived a little bit later, a few seconds later, or quarters of a second, pieces of a second later, got here, aha. What I'm going to do is I'm going to bring these two sets of hard disks together at the computer, and what I'll do is I'll compensate for the fact that light got there a few seconds later, a few milliseconds later, and I'll readjust the timing mechanism. So I'll be able to figure out that this ray of light, which got here at this time, I can figure out when that ray of light got to that telescope, and I'll use the same ray of light, just moving the tape head up so that they're the same, and they overlap, and they can be combined. But now I'm combining data from one side of the Earth and the other side of the Earth, and that gives me a telescope that is as big as the Earth, because I've used telescopes all over the Earth that are giving different pieces of that same light ray, and it essentially gives me an aperture that is big enough to resolve something that is that small. The bigger the bigger you build a telescope, the better you can see things, right? The sharper the images. And if you build something as big as the Earth, you can get something as sharp as you can. And if you're looking at a whole black hole 53 million light years away, you can see it. Did you have a question?
Is this the present day, the most ultra-modern telescope in existence now?
Remember, the telescopes are, is this the most modern telescope in existence? No, remember that these telescopes are pre-existing. They were built for other purposes. Some guy, and by the way, if you ever see the videos, and one of the things in my links is one of the guys who created this project, and he is so well spoken, it's incredible. He invented the idea of doing this. I'm not sure it was only his idea, but anyway, he got the project going, and essentially all that's been done is an idea that has been followed up on by 200 people using existing facilities to put it together, and new software to do it. The hardware is old. The software is new. The idea is new. Yes.
Do we know the exposure time?
Yeah, the odd thing about this is the exposure time is like 7 minutes.
7 minutes?
It's not like 42 hours, which you would think, because I think M87 is one of the very brightest things in the sky when it comes to radio waves. If your eye could only see radio waves and nothing else, you'd look around you, and maybe the Empire State Building would be broadcasting something, and you could see it, the tower, and you might be able to see the radio waves from that. But really, the brightest thing in the sky is M87 and also the center of our own galaxy is the brightest things in the sky. So you don't really need a lot of time to add up the power of
You
it.
could have made a video.
What?
You could have made a video instead of having a still picture.
They have made a video. They've taken the same image a few times. So they have like 4 different
Frame.
frames for the thing, and it literally brightens and dims over time in minutes. So yeah, you can get, probably could be a very cool video, you know, because all they have to do is spend a lot more computing power on this, and they probably will now that they've gone through the process of testing it. Yes.
As you get closer to a black hole, does the atmosphere or the space area, does it get lighter? I mean, does it get brighter and hotter?
There's one other thing I didn't show you, which really does it get brighter and hotter. So if I could show you this, this one, this is what. Hopefully, this will show up.
This.
Okay, this
Ring.
is what I wanted to show you.
Lens.
To me, this is.
That is the event horizon.
This is, we have all thought, for some reason, that the black hole image that we are seeing is of gas that seems to be going around, okay? And somehow or other hot, okay? And it is hot. And the reason it's hot is because the molecules or the ions are hitting each other, and so the temperature is high. So that is true. But what we're going to see here is that how that picture was made. And I have to tell you, when I saw this little piece of video, I was surprised, and if you may be surprised as well to see how that picture, where those photons that are in that picture, where they actually came from. They're not coming from what you think.
The matter and light sort of whirling around in that shape, but it's actually more complicated than that. It's really more. Well, talk us through this animation, because it's light being lensed around it.
So you'll see here that some light from behind it gets lensed, and some light there's a loop-to-loop around the entire orbit of the black hole. But when you get enough light from all this hot gas swirling around the black hole, then you wind up seeing all of these light rays come together on the screen, which is a stand-in for where you and I are, and you see the definition of this ring begin to come into shape. And that's what Einstein predicted over 100 years ago.
Yeah, that is amazing. So tell us more about what.
So that is it. That's it. And because it stuttered at exactly that moment, you may not have been as impressed.
Where you and I are.
There it is again.
And you see the definition of this ring begin to come into shape. And that's what
It stuttered
Einstein
again.
predicted over 100 years ago.
Yeah, that is
I'm going to
amazing.
try it one more time.
So tell us more about what we're actually.
One more time, if we're lucky, and we're not. But did you see it?
Towards us below and receding from us on the top. And just as the train whistle is a higher pitch when it's coming towards you, there's more energy from the gas coming towards us than going away from us. So you see the bottom part brighter because the light is actually being boosted in our direction.
And how
Anyway,
physically
so
big
that's
is
it.
that?
I mean, that's all I'm going to try for.
Would fit well within that.
Okay. So that's the idea of the black hole. We can talk about it next week as well, if you want, because there's more to talk about. But for right now, that's the sequence that I was planning to do. So is there any more questions that we want to do before I conclude? Okay, good. So with any luck at all, you will see this class on the web before next week in the Laird Whitehill channel on YouTube, because that's what I've been doing recently. And you're not on it because the camera's facing me, so I don't need to get press releases from you. If you have not signed the attendance sheet, it's a horrible one this week, but if you haven't indicated your name in any form on it so I can compare it to the normal attendance sheet, please do so. And I'll see you next week. Okay? Good.